Hello and welcome back to Calculus 2, section 6.5 on length of curves. So you have some function on the graph of a function in a coordinate system, and you would like to know the length of that line. So here we have some f of x, and say you are not able to stretch this one and figure out the length of it by putting it against the straight edge or ruler. So we have to figure out the way to compute this. So say we take a small delta x cut in this line. Now, delta x is the width of that representative rectangle, and that is always small. So what I have over here is the little delta x cut, which you probably can't even see. That creates delta L in length. So what I'm going to do is I'm going to take this little piece here and bring it up right here in this much larger picture, where we are going to see that we have delta y for the height, delta x for the width. We have delta L, which is the length of the curve we are interested in, and then we have the length L, which you can calculate by basic Pythagorean theorem of delta x squared plus delta y squared. So these are the measurements. So all I did is I enlarged this little segment here, so it's just zoom in, and we write Pythagorean theorem for this piece. So now I have my L over here as a square root of delta x squared plus delta y squared, and I'm going to multiply this by 1 in the form of delta x times delta x. And now I'm going to take 1 over delta x and ship it inside the radical, and this delta x that is in the numerator will stay outside. So L equals square root of 1 over delta x squared, because when you stuff it under the square root, it picks up a square, and you have your delta x squared plus delta y squared, and you have delta x left on the outside. Now, when you multiply here through, when you distribute, you get that L is equal to square root of 1 plus delta y over delta x, everything squared, and then times delta x on the outer side. This is the length of one single infinitely thin piece of your curve. And what we are going to do now is we are going to add them, all of them together, all infinity of those together, by putting up a sum and limit, which turns into integral. So this formula turns into the length of curve formula, where we have integral a to b square root of 1 plus the derivative of the function squared dx, and its partner in crime, L equals integral c to d 1 plus f prime squared of y dy, if the function is in terms of y. So these two formulas represent the length of curve, and the lecture is over. That's it. So all we need to do now is, 2-3 examples, and we're done. There are no additional formulas. There is nothing else. These are the formulas that you need to add to your bank. Now, as we discussed a few times in the class, there are absolutely no formula sheet on the test or anything like that. The suggestion was for you guys to write the formulas on the cover of your notebook. So far you have area between two curves, you have disk method, washer method, shell method, and now length of curves. We covered 5 formulas. Your first exam will have anywhere between 10 and 15 formulas to memorize. All of your calculations are Calc 1. So providing you with formulas, then you're technically not doing anything Calc 2. Learning these formulas and the way to set up the integral is all Calc 2 is all about for the first test. So keeping your formulas straight on the cover page of your notebook will be great. That way you know exactly everything you covered. So look for length curve between area between two curves, disk method, washer method, shell method, and then now the 5th formula we're learning. Now each one of these 5 formulas has its X flavor and its Y flavor. So technically, yeah, it's 10 formulas, but it's 5 doubles. They're all the same. Just substitute A and B with C and D and change X's into Y's and you're done. So you are learning only, yes?
So now, this is the 10th formula, or this is the 5th formula? You said there are going to be 10 formulas.
Oh, this is the halfway, because we are going to have revolution. We're going to have some of the stuff coming up. We still have chapter 7, right? So we are today we will be halfway. Yes?
That's the derivative of x squared, right?
No, that's the derivative squared. So you will do the derivative and then you will square the whole. So we're going to do now the example for this and see this at work. So this is the lengthening of curve, either in X or the Y. So what are the cheap problems? Well, linear line obviously is a cheap problem because we can check that answer for the linear line easily using the distance formula. Now, why simple if we can complicate things, right? So instead of using the distance formula, we're going to use the sledgehammer over here and see what the length is and then verify with the distance formula. So say, what is the length for, and then I'm just going to come up with a drawing over here and then so here's the line segment that, let's say, looks like that, ends there. So what do I have? This is a point 1, 2, 3, 4, 5. This point is 5, 2. Starts at 0, 0, 5, 2. What's the length of the curve? Okay. Well, let's use the sledgehammer. We have our A and B from 0 to 5. And I need f of x, which is the equation of this line. And that would be just our standard y equal mx plus b. Your y-intercept b is 0 because it goes through origin. So this is just f of x equals the slope is, rise is 2 over 5. So 2/5 x is plus 0, right, is all we have. So now we have that. We know that we have to take the derivative of this, which is 2/5, and now we can do the integral. So integral from 0 to 5, and now we have our function derivative, now we have our square root of 1 plus, and this is the derivative squared. We just have 2/5 squared dx. So obviously you can't have cheaper problem than this. But then again, you would never use this method for linear line because you know the distance formula. At least I hope you know the distance formula. So I have 0 to 5, square root of, and this is going to be 4 over 25, then 25 over 25, so that's 29 over 25 dx. We can kick the constant square root of 29 over 5 out. The integral of 1 is just x computed from 0 to 5. And the answer over here is square root of 29, because when you plug 5 for x, you will get 5 and 5 canceled. And when you plug in 0, the whole thing dies. So the answer is just square root of 29. And let's say you care, right, about this and you want to check. It's hypothetical. So you would obviously use length of curve, which is the distance formula for straight line. And you would just run the distance formula. If you remember, the distance formula was x2 minus x1 squared plus y2 minus y1 squared. Now your y1 and x1, y1 is 0, 0, and your x2, y2 is 5, 2. So we are going to calculate the distance as the square root of x squared, that's 25, plus y squared is 4, square root of 29, and we are done. And that's somewhat verifying that the problem is there. It's done. It's good. Now I would like to do the same example I did on my last class for length of curves, and that is in the textbook. If you have a textbook, please just jump to 5 real quick, or 6 5. There is a problem that has ln in it, which is awesome. We're gonna 5 problem number 12 from homework. By the way, yes. I'm sorry? This question?
Yeah.
Yes. When I add 1 plus, when I add 1 to 4 over 25, when I square 2 over 5, I get 4 over 25. And then when I add 1, and 1 is 25 over 25, 25 plus 4 is 29 over 25. So that's just adding fractions here. And that whole fraction becomes 29 over 25, and then we kick it outside. Now, square root of 29 stays square root of 29, and square root of 25 is 5, so there is no root on the bottom. And then we integrate, because we took the constant out, we integrate 1, and we get x, and then plug in 5 and 0. Fair? With a smile? Happiness out of primary concern. Yes. All right. Let's take a look. Again, length of curve, problem 12 in a textbook. Now, they did solve out few problems as examples. I'm not going to redo those because you know all the letters and numbers, right? You can read. You don't need a middleman, right? You just go and read the examples that are already done. This problem has the function f of x is equal to, I believe, 3 ln x minus 12. Yeah, I gotta go all the way there too. X squared over 24 minus x squared over 24 minus x squared over 24 on 1 to 6. So those are your A and B, your x1, x2. A and B are 1 and 6. So this is the problem. Problem 12. And let's see. Just because I'm nosy. I want to graph this, see what it looks like. 3 ln x minus x squared divided by 24 so we have the graph displayed now. So I use Desmos to graph this. And what we are calculating here is the length of the line from x equals 1 to x equals 6. So we are calculating the length of this. If you are to take a piece of rope or a string and then carefully use the tape and tape it along the function and then cut at these two locations, then take the string back off, stretch it against the ruler, the measurement you get should match exactly, within the margin of error obviously, match exactly your calculation. Because this particular calculation is literally going to put the ruler against the curvature over here. Maybe you can turn it somehow and then calculate the length of the line, the length of the curve. Now we know to calculate length of curve, we saw the formula. We need to find the derivative of the function and then plug that under the radical 1 plus that derivative squared and then do the calculation. So this is pretty much just grind, right, to do the work. We start with the derivative. You always start with the derivative. So f prime of x is equal to 3 over x, because derivative of ln is 1 over x, and then you have times 3, minus the derivative of x squared is 2x, and then that 2 will cancel 24, so you have x over 12. So this is our function derivative, and now we immediately go for the integral. We have our integral 1 to 6. Those are our limits provided by the problem. And we have the square root of 1 plus 3 over x minus x over 12 squared dx. So the only thing that we can do here is FOIL this, which is, right, applying the square to each. Well, you will have 3 terms, right? Because this is difference of squares. Difference of squares is given as a minus b squared as a squared minus 2ab plus b squared. Your grade usually dies with this term because you forget it for some reason, and then it's game over, for this problem at least. So make sure you have the middle term. So now, what I'm going to do is I'm going to work out this calculation. So 3 over x squared, that it's 9 over x squared. And now I have 2 times 3 over x times x over 12. Because that's 2ab. That's my 2ab term. 2ab. So when I multiply these together, you see that x's die. 2 times 3 is 6, which cancels 12. You just get negative 1/2 here. A whole bunch of stuff cancels, right? And then finally, plus x squared over 144, and then dx at the end. What is the obvious next step? Yes, we will add 1.5. I mean, subtract it, right? So we have 1 to 6 square root of 9 over x squared plus 1/2 plus x squared over 144 dx. Are you ready for a $1 million trick? Now I need you to look at this, because this is the trick that will solve, and I believe you have 6 problems in your homework or in the book. This is one of the 6, I believe, that all have the same thing. All right. If this binomial squared expanded into these three terms with the matching minus, what is this going to compress into? It's going to compress into this with a plus, because the only difference between these two over here is the positive and negative 1/2. If you remember another algebra formula, which is this one, a squared plus 2ab plus b squared condenses into a plus b squared. So if I erase all of this stuff over here, and now the two that are circled, as you can see, they only differ in the sign of the middle term. If you compare the two red equations from algebra that I gave you, those two trinomials are also identical apart from the middle term sign. So this will compress into integral 1 to 6 square root of 3 over x plus x over 12 everything squared dx, and this is where square and square root die, and you have a very basic integral to deal with. 3 over x plus x over 12 dx. Mathematical gymnastics, right? You do a flip, then you do a backflip, right? And there you go. So now, when we integrate, we have 3 ln absolute x plus, when I square this, I will get x squared over 24, everything from 1 to 6. That's going to be 3 ln 6 minus 6 squared over, no minus, plus 6 squared over 24 minus 3 ln 1 minus 1 over 24. 3 ln 6 stays as is. How much is ln of 1? Very good. So we have 36 minus 1 is 35. So plus 35 over 24, and that's the answer. Now you can go and, get the decimals if you want, but that will be the exact answer. The length of the curve is 3 ln 6 plus 35 over 24. And that's it. Done deal. The trick here, that was a good one, to expand, add 1, realize that they're the same, condense into the same problem with the plus, and then square will cancel with a square root. You get the basic functions to integrate, and you go from there. Now this trick obviously only works if you have 1/2 there. If you have anything else, well, when you add that to a 1, it's not going to be by the same number. If you have a quarter there, negative quarter, then this would be a negative quarter, and this would be a positive 3/4, and then they don't condense into the same expression, obviously. So this only works if your derivative squared spawns a negative half as a middle term, because the only case is negative half plus 1 is positive half, and then you just have that one sign difference, so you can switch from negative to positive in a formula. Whole bunch of word problems to compute with this. You want to know the length of curve as you are stretching the cable between two power towers, let's say. That stuff is extremely expensive. If you know those huge metal power towers that have wires attached on both sides. Well, the tower is paired only with one set of wires on one side. The other set of wires belongs to the other tower that is leading to this one. It's $100,000 per tower and a set of wires. So when you see those 10 towers, it's like $1 million right there for installation materials and so on. It's very expensive stuff. You don't, right? And they are carefully computed. We are going to learn in chapter 7 function which actually gives us the shape of the line. It's not a parabola. It does look like it sags a little bit, looks like a parabola x squared. It's not. It's a function called cosine hyperbolic x. And it's a hyperbolic function. We are going to learn that function in 7.3. So anytime you hang a wire, piece of wire or whatever, cord between 2 points, that function it forms, it's cosine hyperbolic. So that's going to be the next thing. Now, I believe they do have a word problem for you to compute that, but they disguise cosine hyperbolic with a different function that it's equivalent. And you will still be computing it for this homework, but they will, I think, put the t for it, so you can calculate the integral. Obviously, once you are there, you will be able to integrate the piece. Now you can. That's 6.5, guys. I hope you're not disappointed. It's one formula and 2 examples, so I guess are enough, and you have a few more worked out in the book to read. When we come back after the break, 6.6, surface area of revolution. We are going to rotate objects again, but this time instead of computing the volume, we're going to find the area of the object for which you can create art and stuff like that. Because you need to give, if you're creating something, you need to give the area to the marketing arts department so they can come up with labels and the design that will actually sell the product. So we'll be back with 6.6 in about 300 seconds.